Hey guys, Mr. Holman here. We're going to start our new unit on factoring this week, and we're going to see that factoring ties into what we've talked about with polynomials the past couple weeks. Specifically, the past couple weeks we've talked about adding, subtracting, and multiplying polynomials, but what we haven't talked about is dividing them, and that's because we don't actually divide polynomials when we first learn about them. Instead, what we use is this process called factoring, where we're actually going to break these expressions down into multiplication problems. There are numerous ways that we can factor, but we're going to take it one step at a time and look at a couple of different ways. And we're going to start with our first way today, which is factoring by the GCF. Now, GCF stands for greatest common factor. And when we refer to the greatest common factor, before we referred to it as the largest number that can divide two or more other numbers. In other words, you've actually talked about factoring before, and you specifically talked about it when looking for GCFs or greatest common factors between two numbers. In our first example here, we have two numbers. We have 18 and we have 27, and we're going to try and find the GCF between those two values. There's a couple of ways that we can do that. One way would be to use what we call factor trees. So a factor tree is where we take the number, let's say 18, and we're going to break it up into two of its factors. Specifically, we want to avoid 1 and 18 because that doesn't really help us. So I'm going to pick two other factors, let's say 2 and 9. I'm going to continue to break these down into other factors, or if I get to a prime number, for example, in this case 2, I stop the branch at that point. But while the 2 stops, the 9 can keep going. So what I'm going to do is split 9 up into 3 and 3. Again, the 3's in this case are both prime numbers because they have no factors other than 1 and 3. At this point, we've reached the prime factorization of 18, which is 2 times 3 times 3, or more commonly, we would write 2 times 3 squared. Let's do the same thing with 27. Again, I want to make sure I split it up into factors other than 1 and 27, so I'm going to take 3 and 9. As we saw last time, 3 is a prime number, so I stopped that branch. However, the 9 can keep being broken down just like we did last time into 3 and 3 again. Once again, we now stop our branch at those two 3's. This means that our prime factorization for 27 is 3 times 3 times 3, or 3 to the third. Our GCF in this case should be the factors that are shared between both of those numbers. And in this case, they each share a 3 times 3, but we wouldn't want to write it that way. We would actually multiply that and say that our GCF is actually 9. You may have learned another way of finding a GCF between two numbers. Perhaps you took each number and you listed out the factors. So for 18, we have 1 and 18, we have 2 and 9, and we have 3 and 6. We want to do the same thing with 27. So our factors of 27 are 1 and 27, and 3 and 9. What I then look for is the largest common factor between both of our lists here, which in this case happens to be 9. So again, this is yet another way that you can find the GCF between two numbers, either using a factor tree like we did over here, or by listing out the factors like we did here. What we're now going to do is apply this idea to polynomials, and specifically we're going to combine these two ideas of a prime factorization as well as listing out all the factors. So let's start with example 2. Here we have the GCF of 6x squared y and 9x cubed y squared. We're going to once again try and figure out what factors do these two values share in common. I'm going to start with the 6x squared y, and specifically what I'm going to do is I'm going to take 6 and break it into its prime factors. 6 has prime factors of 2 times 3. I'm also going to take the variable terms and I'm going to expand the exponents. So instead of leaving it as x squared like we have here, I'm going to expand that into x times x as well as the y. Now let's do the same thing for 9x cubed y squared. The prime factors for 9 should be 3 times 3, and we're going to expand x times x times x times y times y. Here you can see how we've kind of combined the two ideas of the prime factor tree with the expansion of all the factors like we saw on the first slide. And I'm going to look at what do they have in common. So if I'm trying to pair things up, I see that they both share a factor of 3. I see that they each have not just one x, but two x's, and they also each have a y. Now notice this other x and y in the 9x cubed y squared, this x and this y, as well as this 3 and this 2. They can't be paired up with anything, so they're not included as part of the GCF. Instead, the GCF is only the paired factors, which in this case were the 3 times x times y, or more commonly we would write that as 3x squared y. Go ahead and pause the video at this point and try and figure out your GCF for the next example, 14a to the 5th b to the 3rd and 21a to the 3rd b to the 7th. Use the same process that I just used on example 2 and then check your answer. All right, so let's take a look here. Let's start with our first number. We have 14a to the 5th b to the 3rd. So if I take 14a to the 5th b to the 3rd and I split up 14 into its prime factors, I would get 2 and 7. And then I'm going to expand the a's and the b's. So I'd have 5 a's here and 3 b's. Let's do the same thing with our 21a to the 3rd b to the 7th. So 21a to the 3rd b to the 7th has prime factors for 21 of 3 times 7. And then I would have 3 a's and I would have 7 b's. Now you might be saying this seems like a really tedious process because we had to list all those factors. And you're right, this is not necessarily the most efficient way to do it, but this allows me to visually see what matches up. For example, the 7's, 1a, 2a, 3a's, and 1b, 2b's, 3b's. So now if I take my GCF, I have a GCF of 7 times a times a times a times b times b times b, or more commonly we would say 7 a to the 3rd b to the 3rd. Getting back to that process of having to list all the factors, if I don't want to do that, what I should be able to do is come up with some sort of shortcut. And in this case, the shortcut has to do with the exponents. If I look at the examples for 2 and for 3, what do you notice about the GCF exponents compared to what we started with? If I look at number 2, notice my GCF had x squared and y. If I look at the terms, x squared compared to x cubed, y compared to y squared, it looks like I used the smaller exponent for both of those variables. If I want to see if that's the correct shortcut, I also look at number 3. So a to the 5th compared to a to the 3rd, I ended up with a to the 3rd. B to the 3rd compared to b to the 7th, I ended up with b to the 3rd. So my shortcut is to always use the smaller exponent term in a GCF. So we're always going to use the smaller exponent in our GCF, specifically when it comes to variables. That's going to be our shortcut. Now you might be saying, how does this tie into what we did last week with multiplying? Well, let's recall the distributed property. Take a look at number 4. We have 7a times 2a minus 4. Remember, the distributed property says I'm going to multiply both of those things by 7a. So I'm going to take 7a times 2a plus 7a times negative 4. And I'm going to simplify that. That becomes 14a squared plus negative 28a. Or I could also write it as 14a squared minus 28a. While we didn't focus a lot on multiple variable terms last week in our lesson, let's go ahead and try number 5 right now. We're going to take 4 r squared t squared times 5r cubed plus 2rt minus 6t squared. And again, we're going to distribute the number outside to each term inside. Go ahead, pause if you want, and see if you get the correct answer. So when we take the 4r squared t squared times 5r cubed, that should give us 20r to the 5th t squared. When we take the 4r squared t squared times 2rt, that gives us plus 8r cubed t cubed. And when we take the 4r squared t squared times negative 6t squared, that gives us negative 24r squared, but t to the 4th. That would be our final answer. So this is what we did last week with multiplying. Now we're going to see that when we factor by the GCF, we're actually going to do the opposite. As I said at the beginning of the video, factoring is a process where we take the numbers or the expressions and we rewrite them as a multiplication problem. Another way of saying that is we break it down and we write it as a product. Specifically in this case, when we write it as a product, we're going to break it down into a GCF times the leftover factors by reverse distributing. So what that means is if I take 14a squared minus 28a, the first thing I want to do is figure out what is the GCF. So if I look at these two terms, 14a squared and the 28a, I look for the GCF between both the coefficient and the variable. So between 14 and 28, 28 happens to be a multiple of 14, so that means 14 is my GCF. When I look at the variables, a squared and a, I could take an a out of both of those. So that becomes my GCF. The leftover terms end up in parentheses, and we're going to have the same amount of terms as we started with. So if I started with 2 terms here, I should have 2 terms in my leftover factors. The way we do that is we basically take 14 and we divide it by the GCF here of 14, which gives me 1. And I had a squared, but I ended up with just a coming outside. So I want to know a times what would get me back to a squared. Well, that would have to be a. There's our first part of the GCF being factored out. When I take 14a out of 14a squared, I'm left with 1a. Then I need to do the same thing with the negative 28a. So I'm going to keep the same sign, which is negative. And again, I want to divide 28a by 14a. So if I take 28 and I factor out 14, 14 times what gives me 28? That would be 2. The a that was there got factored out. I don't want to put another a here with the 2 because then when I multiply it by 14a, it would become 28a squared. So really, these happen to be my leftover factors. And this is actually our final answer, which is a little weird because we're used to getting nice, neat numbers. But as we saw with polynomials, it doesn't quite always work that way. So here we're going to see that we're breaking it down into a multiplication problem, or what we would have done last week. Let's try another example. Here in number 7, we have 20r to the 5th t squared plus 8r to the 3rd t cubed minus 24r squared t to the 4th. So again, I want to break it down into first my GCF. So let's look at the coefficients. Coefficients happen to be 20, 8, and 24. And when I first look, I can see, well, 20, 8, and 24 are all multiples of 4. So I think that might be my GCF. I'm going to check that. If it doesn't work out, I'll know because in my leftover expressions, which I saw up here, I would still have something that could be factored out. So I'm going to try 4 and we'll see what happens with the leftover expressions. Well, let's see. If I do that, 20 divided by 4 would leave me with 5. Then I have 8 divided by 4, which is 2. And negative 24 divided by 4 would be negative 6. So I think that is the correct GCF as far as the coefficients go, because I can't factor anything out of 5, 2, and 6 other than 1. That wouldn't really help us. Now we have to look at the variables. So when I look at the variables, remember our shortcut here is for each variable, my GCF should be the smallest exponent between the like terms. So if I look at the r's, r to the fifth, r to the third, r squared, the smallest exponent is r squared. So that means I'm going to factor that out. And essentially, I subtract that from each of these exponents here. So that would mean here I would have r to the third. In the middle, I would have just r. And at the end, I wouldn't have an r because I took both of them out. We're going to do the same thing with the t's. If I have t squared, t to the third, t to the fourth, the smallest exponent is t squared. So again, we're going to subtract. Can't do anything here with the t squared because it's already factored out. So 5r cubed is my first term. Then in the middle, I had t to the third. I pulled 2 of them out. That's going to leave 1 more t there. And at the end, we have t to the fourth, but we pulled 2 of them out. That's going to leave us with t squared. And in this case, you can see we have 3 leftover factors. Because if I were to go back and distribute 4r squared, t squared to those terms, I would see that my final answer ends up with what I started with here at the beginning. I would end up with this as my answer. Even though our last example had multiple variables, we're primarily going to stick with one variable. So let's look at example 8 here. We have 2x cubed plus 4x squared minus 2x. Go ahead right now and pause and see if you can figure out first, what is my GCF for each of these things? So what's the GCF between all 3 of those? And let's see if we can factor that out. If you factored correctly, you saw 2, 4, and 2 and realized your GCF was 2. And then for the x cubed, x squared, and x, you said the smallest exponent there is the x to the first. So we're going to bring x out. Then you just had to figure out what were the leftover terms. So we took 2x to the third and we factored out 2x. So 2 divided by 2 would be 1. And we had x cubed. I took 1 away. That would leave me with 1x squared. Then in the middle, I had 4x squared and I pulled out the 2x. So 4 divided by 2 is 2. I had 2x's and I took 1 away. That leaves me with just 1x there. So 1x squared plus 2x. And my last term, 2x to the first, I factored that entire thing out. That doesn't mean I leave this blank here. I have to have something that I could multiply 2x by to get back to that, which means in this case, if everything gets factored out, it's just going to leave me with 1. And in this case, because it's minus, I should have minus 1. That would be our final factored answer, 2x times 1x squared plus 2x minus 1. One of the things that we would find, though, is that this method of factoring, and actually all methods of factoring, don't necessarily always work the way we think they will. If I look at my last example here, number 9, and I look just at my coefficients, the n squared technically has a coefficient of 1, and then I have 2n and negative 5. So if I'm looking at 1, 2, and negative 5, the GCF in this case is just 1. And that would mean the leftovers are 1, 2, and negative 5. But then when I look at the variables as well, I have to take out the smallest exponent. So the 1n squared plus 2n, that's actually 2n to the first. But if I look at the last term, the negative 5 doesn't have an n at all. So I can't factor out a variable if all 3 terms don't have it, which means this stays as n squared in the first part, and the middle part is still 2n to the first. If I look at these 2 things, these 2 answers are exactly the same, which is to say this does not factor by GCF. And that's going to be something that we have to watch out for. Sometimes factoring works really nicely. Other times it doesn't work at all. And that's when we have to look at other methods of factoring. What I'd like you to do today and the rest of this week is to practice your factoring by GCF. You'll see that there is a topic on IXL for you to complete in the Algebra 1 section. And there's also a short, just 5-question assignment on Schoology where I need you to figure out what the GCFs are. So good luck with that. If you have questions, don't be afraid to reach out. And I believe this week it might be really important to jump into Zoom on Wednesday. So make sure that you watch for that link in the folder for our Zoom meeting so that we can go over this together face to face. I hope you guys are all doing well, and I'll catch you later.